We're going to skip over some of the sections in Chapter 10 because they're not in the AP curriculum, and so our next section is on Chapter 10.8. And the first thing is just recognize some of these vocab words. Vaporization and evaporation both have to do with a liquid turning into a gas. Evaporation, we usually define it as happening on the surface of the liquid, and it's at room temperature, which is different from boiling that happens at a high temperature and usually happens within the liquid. So first of all, vaporization is endothermic. And endothermic means that you have to put energy into it to make it happen. And usually when we talk about breaking bonds, that's when we're going to talk about endothermic. So you're not actually breaking bonds when you vaporize something, you're actually separating intermolecular forces, but it's kind of like you're breaking something. So that's how you can remember that it's endothermic. We have talked about vapor pressure before. This is the pressure of a vapor that's sitting on top of a liquid in a closed system. So if you have a water bottle with a top on it, some of that water is always evaporating into the space between the water and the surface, of the lid. And so you have some of that water vapor just kind of bouncing around in that space. And we talked about this when we talked about collecting a gas over water, that you have to correct for the pressure of the gas by subtracting out the pressure of the water vapor. And that is dependent on the temperature of the water. So the hotter the water, the more of it will evaporate, so you'll have a higher vapor pressure. And you can graph the vapor pressure down here. So this is showing you the boiling points for various liquids. And you can plot, 2 lines or 10 lines or whatever, but it's a way to compare different chemicals. So the further to the left they are on the graph, it means the cooler the temperature that it takes to make it go from a liquid to a gas. And then as you go to the right of the graph, those chemicals take more heat to make them boil. So you can compare them, and you can talk about the intermolecular forces based on how easy or how hard it was to make it boil. So in this particular graph, let me just label it A, B, and C so you can see it better. So chemical A didn't take much energy to turn it into a gas, but chemical B took a little bit more, and then chemical C is the most. So I can predict that of these molecules, chemical C is going to have the highest intermolecular forces or attraction because it took the most heat to vaporize it. And you can also talk about the word volatile. Watch out for that word. So volatile means that they evaporate easily. So of these 3, letter A is the most volatile. When you're calculating vapor pressure, sometimes you can use Pivner. Just watch out for the information that they give you in the question. So you can use the ideal gas law there. You can also use it for density. And this is the evening dirt one. Remember, PM is like evening and DRT is dirt. So PM equals DRT is an easy way to remember that one. No, it's kind of tough to derive, so I just prefer to memorize that one. And this is a vocab word that you might not remember from first year chemistry. Sublimation means going directly from a solid to a gas. So if you look at a phase diagram, which phase diagrams are not in AP curriculum for some reason, but on a phase diagram, and what I'm talking about is this graph that looks like this, that you probably remember from honors chemistry. If standard pressure or like normal pressure that you would have just in the atmosphere, if it falls below the triple point, like this, then as you go from a solid to a gas, it skips over the liquid phase because you can see that the liquid phase is above that pressure. And let's go ahead to talk about this heating curve. So for this heating curve, you did this in honors chemistry. This is showing you the temperature change as you go from a solid all the way to a gas. So most people think that solid is the coldest and gas is going to be the warmest, which it is, but it's not a straight line. It's not like you go directly from solid to liquid to gas like that. What really happens is that you are putting energy into it, and at some point, the energy that's going into the substance is no longer speeding up the particles. And remember, temperature is a measure of how fast the particles are moving. And so if the particles are not moving any faster, then the temperature doesn't change. So notice that on this flat line right here, the temperature stays at 0 all the way across, even though you're still putting heat into that ice cube. And so at this point, let's use some different colors. At this blue dot right here, you have a all solid, 100% solid. And as you continue to heat it, it starts to turn into liquid. And then at this green line right here, you have all liquid. But notice that it's still 0 degrees all the way across. So all of the heat that you're putting into that ice cube at that point is separating the intermolecular forces so that instead of just vibrating in place, the particles can flow around each other. And so you have to separate those intermolecular forces to let them flow. And that requires energy to separate those intermolecular forces, and that comes from the heat. But that's kind of hard for students to accept because it seems like when you're heating an ice cube that it should continue to get hotter the more you heat it, right? But it doesn't, because during the phase change, all of the heat is breaking those bonds. It's not, or the intermolecular forces, it's not actually speeding up the particles, and so the temperature doesn't change. And then once you get to that green dot and you have all liquid, then you can speed up those liquid particles, and they will flow faster and faster until you get to this red dot right here. And at that point, it's going to start to turn into a gas. So from that red dot to the second red dot, it's going to turn into a gas. So we have all liquid on the left, and then as you go across the line, it turns into gas. So you have all gas on the right. And then once you get to that second red dot, then you can heat up the gas as well. And we have equations that you can use for various parts of this graph. So for any of the energy changes that are not changes in states of matter, you can use what we call the MCAT equation. It looks like MCAT. So you're going to use that on any of the diagonals. You would use it here, and you'll use it here, and you'll use it down here. And those letters Q stands for the energy, so that's going to be in joules or kilojoules. M is the mass, C is the specific heat. And that is basically a measure of how well something absorbs energy. So metals have a very low specific heat because it doesn't take much energy to make them change their temperature. So if you put a pan on the stove, it's going to get hot really fast, and it's going to be really hot within seconds. Whereas water has a very high specific heat because it takes a lot of energy to make the water change its temperature. So C is specific to each chemical. So each pure substance has its own specific heat value that you can look up. So usually that's given to you. Sometimes you have to identify something by solving for C. So if they give you Q, M, and the change in temperature, you can solve for specific heat, and then you can identify what the substance is based on its specific heat. And then the last thing is the change in temperature. So this little triangle here is delta, which means change in. And whenever you do a change in, you always want to do final minus initial. And that way you'll end up with the correct sign. So be careful with Q, because remember, for Q, because we care about which direction that energy is going, we have to make it positive or negative, which doesn't mean greater than or less than 0. It means heat is going in or heat is going out. And if you always set up your temperature so that you do final minus initial, your Q will end up being the correct sign when you solve for Q. If it's a solid or a liquid, solid to liquid or liquid to solid. So if you are doing, make a better line here. If you're doing this line right here, so you can go to the right on the graph or to the left. It just depends on whether you're putting heat into it or cooling it down. You're going to use Q equals M times delta H fusion. And the heat of fusion is the energy to change 1 mole of a substance, of a solid, to 1 mole of a liquid. So it's basically the energy it takes to make that thing melt, or the energy you would get if you're freezing it. And this is specific to each thing as well. So this is the kind of thing where they would have to give you that value. And the problem with this equation is that you will always get a positive value for Q because there's no subtraction. You just multiply mass times the heat of fusion. And so what you'll need to do is decide whether or not that Q should be positive or negative, and you can physically put the negative on there yourself. So if it says in the question that heat is being released, or that it's cooling it down, or it's condensing, any of the things that indicates that heat is being given off, then you would put a negative on that Q value. And same thing for the next one, except it's a different phase change. So if you're doing liquid to gas or gas to liquid, so this would be on this top flat line up here. I'll do it in blue. If you're using that line up there, you're going to use Q equals M times H vaporization. And again, they'll usually give you the heat of vaporization. So I don't actually see it on here, but the delta H vaporization for water is 2,260 joules per gram. And so again, you can calculate the amount of energy needed to boil or evaporate or vaporize, any of those words work, a certain grams of water. And again, this one you won't get a negative either. You have to decide whether to put a negative on it. And you can do multiple steps in this graph, which is what we did in honors chemistry. So let's say that you're starting with an ice cube at negative 10 degrees, and you want to heat it all the way until it's steam at 120 degrees. So the first thing you'd have to do is use MCAT to get it up this little first green line here. And notice that the temperature change is not -10 up to 120. It's just -10 up to 0. So you have to stop it at the 0 line. So the delta T there would be 10 degrees. Then you're going to do, I'll do it in blue. So then you're going to melt it, where you'll use Q equals M times the heat of fusion. Then we'll do it in red. Then you're going to use MCAT again. However, you'll have a different specific heat because once you change the states of matter, it changes the specific heat. So you want to make sure you choose the specific heat that matches matches the state of matter that you have. And then the delta T for this one is going to be 0 to 100, which is weird because 0 and 100 were not anywhere in the question. You have to know how this graph works and see that it goes from 0 to 100. And then you would do the second green line. You'd use the mass times the heat of vaporization. And then finally, you could use MCAT one more time, and this time you would start at 100 and go to 120. And then what you would do is add all of those Q values up to get the total Q. Just be careful when you add Q values and make sure that you're either adding all positives together or all negatives. And in Canvas, I posted like a picture of a sticky note that has this graph with the equations on it and all the things that you'll need to solve those problems. Just a couple more things. If you ever see the word normal in the question, normal means it's happening at standard pressure. So just make sure you go up to standard pressure, and then you can figure out whatever they're asking you for the melting or boiling point. And there's a few really cool things, and I posted a video in Canvas of somebody doing supercooling so you can see an example of how it really works. It's a tough thing to do, and you'll see that in the video. He fails the first few times he tries it, but it's where you can make a liquid, you can allow a liquid to exist as a liquid at temperatures below its normal melting point. So it seems like it should have frozen, but if there's nothing for it to form those crystals on, then it won't actually freeze until you shake it or slam it on the table like the guy does in the video that I posted. And then quickly that crystallization will begin. And you can do the same thing with superheating. And then the last thing is calorimetry. And this is where you can, first of all, it's the measurement of heat in or out of a system. And what you can do is say if you have a closed container or a closed system where energy is not being lost, then whatever is losing energy will be gained by something else. And we've set some problems up like this in the past, but we're going to do it again for this chapter. So that the Q gained is equal to the Q lost, except one is positive and one is negative. And so then what you can do from here is to plug in, you can plug in MCAT for these. So you can plug in the mass for whatever is one thing. Like if you, I think the example that we did in our last chapter is if you take a frozen piece of glass and you put it into water, the water will lose energy to the glass. So you would put all of the glass information on one side, and then you put all the water information on the other side, and you can set them equal to each other, and then you can solve for variables. And you'll go through some of these in your homework problems, and you can look in the textbook for some examples as well. And that's it for today.